Kepler's law of planetary motion. This heading is very interesting. This heading is very interesting. Kepler's law is very interesting. Kepler's law of planetary motion. Kepler's law of Kepler's laws of planetary motion. Kepler's law of planetary motion. Kepler's law of planetary motion. Kepler's law of planetary motion. Kepler's three laws of planetary motions are: first law, each planet moves in an ellipse with sun at its focus. This is the figure. You can also show the figure. Okay. Take A, B, and this is the sun. This is the sun, and point P, P dash, P, R, D, theta, D, theta, R2, and R minimum, S, R minimum, and R plus R1 plus R max, R1 plus R max, point A and point B. Okay. Kepler's first law. Each planet moves in an ellipse with sun at its focus. Okay. First point. Each planet moves in an ellipse. With sun at its focus. Okay. Second law. Kepler's second law. The radius vector is that the radius vector is that the line joining the sun, the line joining the sun to a given planet sweeps out equal areas in equal intervals of time. Areas in equal intervals of time. Okay. The radius vector is that the line joining the sun. The radius vector is the line joining the sun to a given planet sweeps out equal areas, swept out equal areas in equal intervals of time, and the third law, Kepler's third law. The eccentricity of the orbit, the eccentricity of the orbit, the eccentricity of the orbit of a particle, moving under attractive, attractive inverse square law, force is given by epsilon square equal to 1 plus 2 Ej square upon mc square. Okay. This expression is we are studying about this expression in previous. So where J is the angular momentum, of the particle, and small m is the reduced mass, E is the total energy, C is the constant, which means case of gravitational force, C equal to G capital M small m upon m, G capital M small m, capital M being the mass of the body about which the particle moves, and G the gravitational constant. Okay, so capital E equal to minus mc square upon 2 j square 1 minus epsilon square, bracket close. This is the equation number 1. Okay, we will go through equation number 1. The equation number 1 is capital E equal to minus mc square upon 2j square 1 minus epsilon square. This is the equation number 1. In the case of a planet revolving around the sun, if epsilon is less than 1, total energy of the system, planet and the sun, total energy of the system, planet and sun, total energy of the system in bracket planet and sun is negative. The planet remains bound to the attracting center. The planet remains bound to the attracting center, the sun. As the planet is bound to the sun and cannot escape from it, it moves around the sun in a closed elliptic orbit. This establishes Kepler's first law of planetary motion. In the case of the motion of planet round the sun, the sun is at one focus, which is taken as the center of the coordinate system of the ellipse. Thus, each planet moves in an ellipse with the sun at its focus, as shown in the figure. The point A The point A where the planet is closest to the sun, where the planet is closest to the sun is called perihelion, and the point B where it is farthest from the sun, which is farthest from the sun, is called aphelion. Second law, second law. Suppose a planet P is moving in an elliptic orbit. Suppose a planet P is moving in an elliptic orbit as shown in this figure. If it moves from P to P dash, in a small time dt, the areas shift out by the radius vector is area of the figure SPP dash, area SPP dash. If dt is infinitesimally small, if dt is very small, then PP dash is a straight line. PP dash is a straight line. PP dash equal to PP dash is a straight line equal to RD theta, okay, and SPP dash is a triangle, and SPP dash is a triangle. SPP dash is a triangle. Okay, the area of the triangle, SPP dash equal to dA equal to 1 upon 2 RD theta, 1 upon 2 RD theta, okay, equal to 1 upon 2 R square d theta. This is the area shift out in a time dt. Rate at which area is shift, rate at which area is swept, equal to dA upon dt. dA upon dt equal to 1 upon 2 R square d theta upon dt equal to 1 upon 2 R square theta, okay. The angular momentum J equal to mr square differentiate of theta and is a constant under a central force, under a central force, okay. So r square differentiate of theta equal to j upon m equal to a constant under gravitational force, constant under gravitational force r1 by 2 r square differentiate of theta equal to j upon 2m equal to constant okay. Hence dA upon dt equal to 1 upon 2mj equal to a constant which verify the second law, the radius vector joining the vector joining the vector joining the vector, joining the radius vector, joining the sun to the planet, sun to the planet, sun to the planet, sun to the planet, sweeps out equal areas, sweeps out equal area, sweeps out equal areas in equal intervals of time, in equal intervals of time, equal intervals of time. In other words, the area velocity, in other word, the aerial velocity, of a planet around the sun is constant. Of a planet around the sun is constant. Around the sun is constant. Okay? That the radius vector joining the sun to the planet sweeps out equal areas in equal intervals of time. In other words, the aerial velocity of a planet around the sun is constant. Okay, third law. And next is third law. Next is third law. As proved above, dA upon dt equal to J upon 2m. Okay? R dA equal to J upon 2m dt. R 0 to capital T dA equal to integration of 0 to T J upon 2m dt, where capital T is the time period of one full revolution. Where capital T is the time, capital T is the time period of one full revolution. Okay? Integrating, we get A equal to JT upon 2m, where A equal to area of ellipse. Now the area of ellipse equal to pi AB. Now the area of ellipse equal to pi AB, where A equal to semi-major axis. Semi-major axis, and B equal to semi-minor axis. Okay? So JT upon 2m equal to pi AB, or T equal to 2 pi MAB upon J. Now B equal to A under root of 1 minus epsilon square. So T equal to 2 pi MA square under root of 1 minus epsilon square upon J, or T square equal to 4 pi square M square A to the power 4 1 minus epsilon square upon J square. This is the equation number third. I the origin is taken as the focus. I the origin is taken as the focus. At the origin is taken as the focus as 2a equal to r max plus r mean. 2a equal to r max plus r mean. Now 1 upon r equal to mc upon j square in bracket 1 plus a j square upon mc cos theta equal to mc upon j square 1 plus epsilon cos theta. This is in previous we would study about the previous of this equation. Okay, so 1 upon r max equal to mc upon j square 1 plus epsilon, and r minimum equal to j square by mc 1 upon 1 plus epsilon. Similarly r max equal to j square upon mc 1 upon 1 minus epsilon. Hence 2a equal to j square upon mc in bracket 1 upon 1 plus epsilon plus 1 upon 1 minus epsilon. Okay, r a equal to j square upon 2mc in bracket 2 upon 1 minus epsilon square equal to j square upon mc in bracket 1 minus epsilon square. Okay, now from the equation number 3 we get, now from the equation number 3rd we have equation number 3rd we have t square equal to 4 pi square m square a to the power 4 in bracket 1 minus epsilon square upon j square equal to 4 pi square m square a cube upon j square into j square 1 minus epsilon square upon mc 1 minus epsilon square equal to 4 pi square m a cube upon c, hence t square upon a cube equal to 4 pi square m by c equal to a constant. Thus the square of the period of revolution of the planet about the sun divided by the cube of the major axis of the orbit is a constant, which is Kepler's third law. Okay, which is Kepler's third law. R the square of time period, the square of time period, the square of time period of revolution of a planet, of revolution of a planet of a revolution of a planet is proportional to the cube of semi-major cube of semi-major axis of the orbit. That means t square is directly proportional to a cube. 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 Okay, thank you. And next is Newton's law of gravitation.